Hello guys, welcome to Madhusar classes. In this session, I'm going to deal with ion exchange chromatography. In this session, I'm going to deal with ion exchange chromatography. So, as a part of Genco syllabus, Genco chemistry syllabus, uh, I am going to deal with this ion exchange chromatography. Now, so what exactly this ion exchange chromatography indicates? Ions are get exchanged in the chromatography. So here chromatography means a study based on colors. Chrom means colors, graphy means study. So how that chromatography will work while exchanging the ions, that we'll see in today's session. Okay, look at this. In the ion exchange chromatography, the syllabus prescribed in the Genco, Chemist exam. The first one, the first point in the syllabus is ion exchange resins. Ion exchange resins. Then we'll move to structure, how the structures look like. Then the equilibria, selectivity, this and all we do. So in the first part, we will discuss a bit less in this video. Then in the second half, you have the remaining parts, like applications, separation of amino acid analysis, separation of rare earth metals, and all those. Okay, so move to the concept. So on what principle this ion exchange chromatography exactly works? So have a look at the principle. Look at this, the separation of charged analytes. The separation of charged analytes takes place on the basis of ionic interactions. So what kind of interactions are playing the major role? Ionic interactions or electrostatic interactions between the analytes. Analytes means the one which you want to separate, and the stationary phase consisting of ionic functional groups. Okay, this stationary phase consists of some functional group. Okay, they are nothing but ion exchanges. Is it clear? So what is the basis for driving force is a competitive ionic binding and repulsion. A competitive ionic binding and repulsion between similarly charged analyte ions or stationary phase ions takes place. So if I show you the diagram how it exactly looks, there happens a competition of ions binding towards the stationary phase takes place. That is a driving force for the separation of ions. Okay. If you look at the type of a resin, the first one, look at this, how resin is manufactured. Suppose I am taking styrene and divinyl benzene. This is 1,4 divinyl, 1,4 divinyl benzene. If they were polymerized together, if polymerization takes place, what happens? So this kind of a three-dimensional structure is formed. Here this is styrene, this is divinyl benzene, styrene, divinyl benzene. So like this, the chain is goes on extending. Okay, so this is how a big polymer is formed that acts as a resin. Is it clear? So the above structure is repeated. The structure is repeated, and it becomes a three-dimensional map. So total cross linkages are determined. This point is important here. The total number of cross linkages can be determined by the ratio of divinyl benzene to styrene. By the ratio of divinyl benzene to styrene. So how these cross linkages are forming? It is based on the number of divinyl benzenes and styrenes you are taking as a reactants. So based on that, how far your cross linking will extend, that can be decided. Okay. Now, in generally, okay, in generally, 10% of divinyl benzene is used in general, okay, for normal manufacturing of resin. So the particle size, the resins is now called as a particle, say, for example. So the particle size of the resin is mainly determined by extent of mechanical agitation, So how, okay, nicely or homogeneously you are mixing it, that is mechanical agitation. So based on that, the beads or the particle size is dependent. Is it clear? Now, before discussing this slide, I'll show you how a polymer looks like chemically. Let's see. This is the structures. So here, first you have got cation exchange resin and anion exchange resin. So resins are two types in general, cationic and anionic. So cation exchange resin CER, anion exchange resin AER. Okay, now look at the cation exchange resin. Cation exchange resin. What does it mean? Cations are get exchanged in this resin. Is it clear? So your SO3 minus is there and H plus is there, suppose. So this part of H plus is replaced by any other anions, cations that are present in hot water or seawater, whatever. Okay. So this, the number of H plus ions are replaced by different cations. Look at this. So in this structure, this is the main skeleton and these are branching is taking place. Okay. 1 second. Yeah. So here, this is a main structural framework and to this aromatic ring, there is always some branches extending from both the ends. Is it clear? So here, if you observe the structure, so what sites are exactly involving in exchange process? Only the active hydrogen sites. H plus ion sites are only involving in exchange process. So if you increase the number of H plus ions, that means increase the sulfate ions, SO3 minus H units in aromatic rings. So the effectiveness of resin can be increased. So how effective your resin means, it depends on number of H plus ions present on its skeleton structure. Is that clear? Now look at the anion exchange resin. Here they have given Cl minus. It is sometimes shown as OH minus also. OH minus also sometimes it is shown. So here again, look at this nitrogen. This is connected to one carbon and three methyls, CH2 and three methyls, total four. Four means it is already in positive charge. Nitrogen, it can carry maximum 3 bonds. If a fourth bond comes in, the lower pair is donated already. So it carries a positive charge. So now here Cl minus, or you can take OH minus. It depends on the manufacturing method. So here, what is replaced? What is the name of this? Anion exchange. Anions are get exchanged by this. So what kind of anions? It may be sulfide, it may be chlorides, okay? It may be bicarbonates. So these kind of anions are get exchanged by anion exchange resin. So in the cation exchange resins, cations are separated, whatever the impurities present, and in the anion exchange resin, anions are separated. So what is left? Only pure H plus and OH minus ions. So from cation exchange resin, H plus will come out. From anion exchange resin, OH minus will come out. So together they will give you a pure water molecule, isn't it? Liquid water molecule. Now, after discussing this ion exchange resin, now I'll go back to the previous slide. Let's see. Yeah, here, how these cation exchange resins are manufactured. It's already there in the diagram, but look at the theory part. Cation exchanges. So here they were easily introduced. We can easily introduce this acidic functional group. What are the acidic functional group present in the cation? SO3H, right? So it is done by sulfonation technique. So sulfonic acid group is attached to, okay, aromatic rings. So that is how a cation exchange resin is formed. Now, the remaining theory part you read, that is what exactly there in that pair. Okay. So weakly acidic cation exchangers, if you are trying to make a weakly cation exchange resin, acidic cation exchanger, weakly acidic, that means weakly acidic, say one example of weak acid, CH3, COOH, CH3COH. By using this, okay, that means if you want to manufacture a weakly acidic cation exchange resin, you have to use a weak acid, that's it. So by introducing this carboxylic acid functional group on polyacrylic acid matrix, that means polyacrylic acid means same, that styrene and other divinyl benzene. So you can finally get a cation exchange resin that is weakly acid. Is it clear? So exchange capacity of the resin mainly determines by H plus ions. Okay. The total number of equivalents of the replaceable protons. Total number of replaceable protons. Is it clear? Total number of replaceable protons. That means H plus in cations per unit volume of resin determines the exchange capacity. I also mentioned earlier. The capacity or efficiency of a resin depends on number of replaceable H plus ions. If there are more number of protons replaceable, then its effectiveness will be more and more. Okay, and these weak exchange cations, these weak exchange resins have a capacity pH pine will depend on the capacity of the exchange resins may also depends on the pH. So if you alter the pH, its capacity may increase or decrease. So this kind of situation may arise if it is weakly acidic cation exchange resin. Now look at the anion exchange resin. Anion exchange. So here OH minus ions will decide the capacity of resin, right? Exchange capacity of the resin is determined by OH minus ions. Suppose if you are trying to make a strong cation, anion exchange resin, a strong anion exchange resin. For that, what kind of groups you have to introduce on the aromatic rings? That means you have to use tertiary ions. If you are trying to prepare a weak anionic exchange resin, you have to use secondary amines introduced. Okay, you have to introduce this kind of different amines to get different exchange resins. Whether it is strong or weak, that you decide by introducing different degree of amines. So the same theory part is there in the para. Have a look at that. Now I'll move to the next slide. Okay, guys. Now here are the some differences between the cation exchange resin and anion exchange resin. These are mostly I have covered in my discussion. Okay. So now look at this. What is the basic thing in cation exchangers? A negatively charged is fixed onto the substrate and exchangeable positive ions. So if you look at the ring and sulfate ion, SO3 minus is fixed to the aromatic ring, H plus is loosely bound to that. So where sulfate area is fixed and H plus is able to exchange, isn't it? Am I right? I'll show you that. Look at this. Yeah, SO3 minus is strongly binded to the aromatic ring, whereas H plus ions are loosely bound. In that area, your cations get exchanged. Is it clear? So now in the anion exchange resin, here positively charged species are fixed to the aromatic rings and exchangeable negative ions, isn't it? Now it is just reverse of the cation exchange resins. Let's see here. I'll, I'll write here. Look at this. Here NH3 plus N or 3 plus is directly binded to the aromatic ring, and the Cl minus is exchangeable, and this positive charge is fixed to the stationary phase, isn't it? So this spot Cl minus or OH minus spot is able to get exchanged by anions. Okay. So now again, cationic exchange resins are two types: weak and strong. Weakly acidic or strongly acidic. Here anion also same, weakly or strongly. Classification is there. Okay, weakly basic and strongly basic. For that, what you need to do? Secondary and tertiary amines you have to introduce into the resin structure. And pH range also will affect the working capacity of the resin, isn't it? Okay, so now look at this common equation. This S indicates stationary phase or resin bed, resin structure. These are the loosely bound areas, COO minus and H plus. When it is reacted with the NaOH, that means we are trying to prepare a weak acidic exchanger. Why? Because COOH group is there. So whatever, weak or strong, whatever. Okay, but this is how the equation is given. COOH, H plus is replaced by, okay, Na plus here. So now this is also structure. Here instead of H plus, Na plus is given. Is it clear? So here sodium plus is captured in the place of H plus. Okay. So on the other side, yes, NH2 plus HCl, NH3 plus and Cl minus. Okay. So this is how the resin structure looks. Okay. So these are the basic differences between the cation exchange resins and anion exchange. Now we'll move to the next slide. See, this is a summary of the types of exchanges. This summary is very, very important. From this table, you may expect a question. Okay, the question can be asked like this. If you introduce quaternary amines in the resin structure, what type of exchange resin may be prepared? Okay, may become. So it is a strong base anion exchange. It is a strong base anion exchange. If you use quaternary amine, strong base anion exchange. If you use simple amine, what you're getting? Weak base anion exchange. If you use carboxylic acid is a weak acid. So definitely you will get weak acid cation exchanger. Because in the carboxylic acid, COO minus and H plus is there. So it is a cation exchanger. That's it. Isn't it? So weak acid cation exchanger is formed. Next, if you use sulfuric acid, it comes from sulfuric acid, right? Sulfuric acid is a strong acid. So there is a possibility of getting strong acid cation exchange. So these are the different types of ion exchange resins. So by introducing these kind of functional groups, you are going to get a different, okay, types of exchanges. So their functional group and their type and examples of that functional groups to try to remember. Okay. So focus little more on this particular slide. Okay. Next. Ion exchange resins. What exactly happens in the column? Look, this is a column. Okay. This is a column, and you have put some solutes or analytes that you're trying to separate them. Okay. So this is a bed, okay, stationary phase. Whatever it is filled, that whole structure, the whole column is filled with some stationary phase. So what happens now? Suppose there are 3 different samples. Say this is first type, blue color second type, and this orange is third. You are trying to separate 3 different samples at a time. 3 different samples. They were present as a component mixture. You are trying to separate them. So you kept that all the sample, or you have poured that sample in this, okay, column. So what happens? So which one will come outside first? From the exit of this, which one will come first? I already gave numbering for 1, 2, 3. Okay. So look at this orange one. Less charged molecules bind less strongly to the resin. If that analyte particles are less charged, that means only +1 or only -1. That kind of charges. Okay. Okay. They will come outside very fast. They are eluted very sooner. The rapid elution takes place because there is a less affinity between the your particle and the stationary phase. Look at this on the other side of this. Look at these diagrams. Anion exchange resin negatively charged analyte anions. They were attracted to the surface. That means this is the stationary phase. On that stationary phase, okay, the particles are get attached. If the charge is more, the more strongly they get bound. If the charge is less, they were less tightly bound. That is very simple, right? So, the one with which carries a more highly charged, okay, they are tightly bound to the stationary phase. So if they are tightly bound, what happens? Their traveling, okay, becomes reduced, or their traveling is slow. They travel slow. If they have more charge, more tightly they were bound. So their traveling phase is also slow. So they come late, isn't it? So, and moderately charged particles will come in between the less charged particles and more charged particles. Okay. Now, if you take a graph of this, okay, 1, 2, 3. Okay, this is a time coming out from the column. So which one is coming first? The third one is coming first because it is less charged, this orange species. See, as soon as you pour the sample in the column, so this, look at this, the pink one and the blue one and the orange one. Orange one is coming very fast to the downside due to gravity or less charged particles. Okay. Due to less charge, less affinity, so less binding to the stationary phase, so it is coming out sooner. So after that, second particle, that is blue one, is coming. After that, first one is coming. So the separation is very clear. The peaks are separated by, okay, little distance. So you can say that that component is having 3 different samples. Okay. So in the ion exchange resin inside, if you see, the elution depends on the charges. More charge, more tightly bound, so travel slow. Less charge, okay, less tightly bound, less tightly bound, I'm saying, okay, less tightly bound, and they come faster. So the one with less affinity with the stationary phase will come out from the column very early. Is it clear? The one with the high charges, if a molecule carries maximum charge, +3, +2, +4, they get tightly bound by the stationary phase. So their traveling, okay, is slow. So they come out from the solution very late. That's why I kept the line at the end. 3, 2, 1 elution order. Okay. Again, you have to look at this. Now I'll move to the next slide. Look at this important properties of resin. Here, in the previous slides, we have seen how a structure looks like and what exactly happens inside the column. Okay, and how resins are manufactured and what kind of resins you can prepare by using different functional groups. They are weak or strong or cation or anion. So after seeing all those, so whatever you do after preparing a resin, it should have some important properties. So that properties were summarized in this particular slide. So this resin properties will discuss in the part 2 of ion exchange chromatography. Hope you enjoyed the session. Thank you all of you. Okay, now you can go to the next session and continue your preparation. Okay, thank you. Bye bye.